So I want to start talking about something we'll use a lot, so-called tight binding method or model. But like for warm-up, I want to consider something even simpler. Let's, as a warm-up, consider double valve potential, of course, in quantum mechanics. And potential is something like that. Potential is, I don't know, something like, if I can draw, okay, something like that. So now this one is V of X, this one is X. So in compared to like usual harmonic oscillator, you have two minima rather than one. Like you can write some functional form for this V of X, but we are not interested. We are not going to solve this anyways. And there's like some left minima and there is some right minima. So this is symmetric double valve potential. For example, classically, there are like two degenerate configurations. If you have like a ball, you can put the ball here or there, and they are like indistinguishable classically because right and left, no difference. Quantum mechanically, like let me write a simpler Hamiltonian, like a simplified model of this system. It's going to be something like this. H is equal to, there is some energy on the left hand side, epsilon naught, and the state on the left hand side, I'll show it like this, left, and the same thing for the right hand side. And they are, since they are symmetric, they are going to have exactly the same energy. So this is right and right. And I also want to, like, the electron starting here can tunnel to here or tunnel the other way, right? I'm going to write some T times left to right or right to left. Okay, I think people have seen this, right? This is just a two-level system, and two-level system is what we like because we can solve everything about two-level system.
Why it's written like that?
Which one? The last term?
Yeah.
Like this is like so this bracket notation, this notation is famous because when you take I, J, right? I, H, J, it automatically tells you the matrix element. So in this case, I and J are going to be left and right. For example, when you write it in this form, I think Dirac invented this formalism. It's going to be, for example, left is going to give epsilon naught, right is going to give epsilon naught, left is going to give T, right left is going to give T. You automatically read the matrix from the equation. It's very convenient. So that's the question, right? Okay. And actually there's another way to write this, which we are going to use more often. It's related to something called second quantization, but you don't have to know that, right? This is just, so we want to make calculations quickly and efficiently, and this actually helps us. And for this, you can think about a harmonic oscillator here and harmonic oscillator there, and it's going to have, and all we care is the ground state of harmonic oscillator. They are like excited states, we don't care about that. So it can be something like epsilon naught, A left, dagger, A left, right? This is exactly the harmonic oscillator you learn in quantum mechanics. And exactly the same thing, epsilon 0, A right, dagger, A right. And there's also this T term, which is going to take something from left and put it to right, or it's going to take something from right and put it to left. Okay. And the matrix form, let me write it. The matrix I already explained. It's going to be epsilon naught, T, and epsilon naught. And we want to find the eigenvalues and vectors. Let me scale this entire thing with epsilon naught. And this is going to be, right, is another way of saying that is, let's take epsilon naught to be 1. So this is 1, 1, and we are going to look at this problem as a function of t. For t is equal to 0, you have like isolated harmonic oscillators. And as you turn on, you couple these two harmonic oscillators. And this, actually you can do it with hand, but let me abuse Mathematica, which is open here already. So here's the Hamiltonian. This is 1 t t1, and I want to show you the matrix form first to make sure I don't miss any factors. Yes, this is not. Oh, I think I defined t in the beginning, so let's delete that, and I can come here. Okay, this is 1 t1. Hopefully you can read that. It's a little tiny, but okay. And what I want to do is I want to find eigenvalues and eigenvectors of this thing. And this one is, I think, eigensystem. And what this says is like, I think the first one is the eigenvalue, right? This is 1 minus t, and the one corresponding to this is like minus 1, 1. This is not normalized. And the second, okay, let me write this. So let me call it lambda 1 is equal to 1 minus t, and psi 1 corresponding to this is 1 minus 1, or minus 1, 1, doesn't matter. The second one is lambda 2 is equal to 1 plus t, and psi 2 that corresponds to this is 1, 1. And which one is the ground state? Which one is the lower energy in this case?
1 minus t.
Right? It seems like, but here we didn't decide the sign of the t. Right? Now we have to, so we are adults and we have to sit down and agree on the sign of t. Determine sign of t. And okay, also before determining the sign of t, let me also like show you the, so these are like states, but in real space what this says us is like there's like there are like these two minima. So 1 here means you have like this, 1 there means you have something like this, and if the sign in between is like negative, what this means is like you are going to have this asymmetric combination, whereas the sign between them is like going to be 1, so it's going to be like this symmetric, right? That's why sometimes, just to remind us, let's put this asymmetric here and asymmetric here, and this is symmetric, and this is asymmetric. Sorry, this is symmetric. And there are many ways to determine the sign of t, but the one I like is the following. Suppose I continuously bring these two wells together. If you want, you can think about this problem like a hydrogen molecule, and you bring these two hydrogens together, and when there's like a nucleus of one hydrogen here, another here, or like you can think about combining these two wells to a single well, and when x left minus x right, or it goes to 0, problem goes to what? Usual harmonic oscillator, right? Of course, it's also a harmonic quantum. And in the usual harmonic oscillator, right, we know the ground states. Right? The ground state is this, right? So this is the ground state of usual harmonic oscillator. And we also know the excited state. If you want, this is psi ground state. Let me put 0 to remind you this is and this is excited 0, and it is going to be this, right? One is Gaussian, the other one is like this, and the third one, there's like one node here, right, in the excited state node. And if you want to be comfortable, there's also third excited state. There are going to be 2 nodes, and so on. But this picture is telling us as x left minus x right goes to 0, I expect lower energy to go to ground state of this system, and higher energy go to the higher energy of that system, right? And this argument tells us this thing has to be the ground state, right? The symmetric has to be the ground state. Otherwise, things do not make sense in this limit we considered. And this has to be the excited state. Then we have to say that, okay, this in this form, it seems like this is the ground state, but now we figured that t actually has to be negative. And better way to do this is like just go here and take t to be positive and write minus here, and put a plus here, and put a minus here. Okay, so this is the ground state. So there are other arguments. Of course, you can, for example, you can consider uncertainty, Heisenberg uncertainty. So what it says is like you want to reduce the energy, right? How do you reduce the energy? So by increasing delta x, how do you increase delta x? You let a little bit of particle to go to the other valve, then delta x is going to increase. Then this is going to decrease delta p, but something decreasing delta p is going to reduce energy. You can think about a little bit about this. Another argument is like nodes. So typically, if you have like a node like this in a wave function, so there's like a node, and there is like a big change in the wave function, right? Because something happens 0, whereas in the other one there is no node. And typically nodes cost energy because you take the gradient, right? Like gradient, like in the Schrödinger equation, and they cost energy. So ground state generally has to be nodeless. There's like I think a famous theorem saying this more systematically, I think due to Feynman, but we don't need that, so let me not get into that. And another observation here, so okay, I think most important is T is hoping is T is called hopping, or T actually comes from tunneling amplitude, and we know in the Hamiltonian it has to be negative. And another observation is classical ground state degeneracy is split due to quantum. If you want quantum tunneling, like something classically can be degenerate, but quantum mechanics is not necessarily so. Good. So this was like a warm-up for double well potential. In the more general tight binding model, we are going to model crystal to be like infinite well, right? There are like many wells, and atoms are going to be localized in each well to lowest order, and there will be like small tunneling. And since tunneling is already small, we'll only consider tunneling to nearest neighbor, right? In some model, we can also consider tunneling to next nearest neighbor and so on. But to understand this, let's start with the nearest neighbor tunneling. Okay, any questions? Now, tight binding. So what our starting point is electrons are localized at site J.
Hocam,
Mhm.
what's our motivation to pipeline?
Because you can see, like, you don't want to go and solve Schrödinger equation every time, right? Like, there are like several reasons for not doing that, right? First of all, it is awkward, right? Like, it is like you don't want to go form these like big matrices, diagonalize, take the corresponding eigenvector, and then work with it. It is not what you want to do every time. Another thing is, like, typically you don't know what potential is, right? There's like some atom, complicated things happens. We don't know it, and they actually don't matter, right? There is some potential, like, for example, exactly like this double valve. I don't have to know the potential, right? If I'm interested in the low energy physics, I know this is what's going to happen. You don't have to, I don't have to go and write, oh, here's your potential, x square minus something something. We don't need to do that because we want to understand things a little bit more economically. And tight binding model does it very nicely. Once you get the hang of it, calculations are faster. It's like results are like simpler equations that you can write, like cosines and sines. And you can take the derivative to find the velocity of blow functions and things like that. And also, that's what actually happens in interesting materials. Interesting materials are not like alkali metals, for example. Interesting metals are like, for example, transition metals. And transition metals, the starting point is generally not a metal. It is like a localized electron that tunnels in the crystal lattice. So there are more motivations, but for the moment we will just outline the method and see how it works. Okay. So by the way, this is, I think, some chemists call it is not exactly the same method, but it is related. They call it LCAO, linear combination of atomic orbitals. And let me set up the notation. So this J is atomic orbital at site, if you want Rj, sometimes I'm not going to write vectors at some point. And what this means is, if you take in the Dirac notation, if you do this thing, it's going to give you the ground state at site Rj. And this is, if you want, you can think about this like ground state of hydrogen atom, for example. Now we need the, this is our starting point, but the states we write has to obey the Bloch symmetry, right? Translation symmetry is not something you can give up. It has, whatever you write, it has to have that symmetry. And we can do that by consider, let me write and explain. And this is very generic. So this psi of Q, let me take it n cells and sum over all sites and multiply each one with e to the I q rj. You can generalize it to a vector form in arbitrary dimension, and this is j. Okay. And psi q of x is going to be x psi q, and this one is going to have exactly the same form above. I just need to have this xj, but xj is written here. It's going to be phi 0 of x minus rj, and rj is, if you want, j times a.
I didn't get this inner product notation.
So this is like nothing to worry about. Like there is like a reason for this. Like, right, these are like I think like in the Dirac notation, states are like vectors in like an abstract space. It's called Hilbert space, and the vectors in Hilbert space, we are showing it with like this. And to write these abstract states in a given state, right? In like, for example, x, I can write it in x space. I can write it in p space, momentum space. I can write it in any other, for example, harmonic oscillator space. Typically, we have to take this bracket with x, and this is by definition psi I of x. This gives you a wave function.
So
The-
just produce-
Yeah, it just produces the wave function for you.
Oh.
And I think at this moment there is nothing else to know about this. If you take bra of x with the state you want, it gives you the wave function corresponding to that state. Okay. I think this is a little bit beyond undergraduate quantum mechanics, but I really believe it's so simple. You have to see this, right? It's nothing to worry about. Like I think it's more psychological than like any. There's nothing technical here. Now I want to show you the Bloch form of this function, the psi q. By the way, I could start with this and completely bypass this bracket notation, but I think it's valuable to get used to bracket notation. If you don't like bracket notation, just erase all these bras and kits and start with this. This is exactly what you do. Is like you have atomic orbitals at a given site, and you shift them, right? And you sum over all. But if you just sum over that all, you have like a periodic function. Not only that, you multiply with e to the I k rj each one. And in the case of symmetric valve, that factor is just -1, right? In the ground state, we had this. +1 and -1 and +1, right? Which can be like e to the I pi or e to the I 0. Here it becomes more general. It's like some phase factor. It can depend on the given site.
Phases are periodic, isn't it?
Yes, we'll see. It is periodic, but like in a way that satisfies the Bloch condition. That's what I'm trying to see now. Let me just write this, and just wherever I see x, I'm going to write x plus a. So this is the only place I see x, and I'm going to write x plus a. And this is a sum over all possible sites. And here, what I can do is like, let me rearrange the site label. I can do rj prime is equal to rj minus a, which is actually equal to rj minus 1. Good. Then, wherever I see rj, which is here, I need to write j prime plus a, but rj prime plus a is going to be rj prime plus 1. Now I can rewrite this sum. So this thing so this is rj prime plus a, and this one is minus rj prime, and the summation label is exactly like we change integration variables, we change the summation variables, and it is j prime. And now I'll take this e to the ik outside. Let me write it one more time. So this thing, erase from here and put it in front. E to the I q a. But j prime is now just a label, right? I can put dummy labels, can be anything you like. And what remains here is exactly what we started here, this wave function. And then it is going to be e to the I qa psi q of x, right? Then we, okay, this is a little bit ugly, sorry about that. So this is q, this is a. Then we show that this function we wrote, psi of k plus a, is equal to e to the I qa psi q of x, has the Bloch form.
Okay. How can we define the summation form here? Consider blah blah blah.
So this the first summation, this guy,
How can we define it? How can we dictate it actually?
like we don't dictate it. I'm asking you is like give me the atomic orbitals, right? Give me atomic orbitals. You give me the atomic orbitals. They can be like ground state of like hydrogen, but they can be any crazy function you like. And I write these functions. Right, this is the function you give me, and what I say is like I just translate this function arbitrarily many times to all over sides, right? And not only that, I also like multiply this function you gave me with this e to the iq. For example, if this side is 0, 0, e to the iq. If this side is 1, e to the ik1, e to the iq to a, and so on, right? I just write, I can rewrite, right? I can use what you give me and generate another object, and that's it. And this object is nice because, as you can see, it satisfies the Bloch condition. And it is the correct function to work with. Otherwise, you are not going to have the most important thing in the solid is periodic periodicity. We can also, like from here, if you remember, we can also calculate Bloch u functions, uk of x. If you remember, we just multiply it with minus and take this psi q. Psi q. For some reason, Gerwin Young converted from k to q here, and I'm just sticking with his notation, with their notation. And this one, for example, is going to have uk of x plus a is equal to, oh, okay, this is q. So this is q, sorry about that. This one q, right? Yeah. Okay, thank you. And this one is uq of x. Okay, any questions? Now, all we did is to write a faithful psi, right? A psi that gives us what we want. And now I can use this psi to find the energy, right? E of q is going to be equal to, I'll just write expectation value of h. And since this psi of q may or may not be normalized, it's always a good idea to normalize it by force. If it's normalized, this is going to be 1 anyways. And once we find this object, this is going to be, since psi is correct periodicity wave function, E of epsilon of q is going to be the correct dispersion with Brillouin zones and everything. So our job is to calculate this thing in several steps. It looks simple, but it requires a little bit, it's like a thorny calculation that requires a little bit work. Any questions? So, okay, I'll calculate this and I'll call it a day today. But I need maybe 10-15 minutes. First, let's start with this psi q is going to be, let me just write it, right? I think we know the form. There's like 2 square roots, they combine to 1 square root, and we are going to have like this j prime j, and it is going to be minus iq. I like writing it like ij minus j prime, and this is going to be j prime j, right? I just took the definition here, so this definition, and I formed the bra from the ket, and I take their inner product. And one I wrote with j, the other one I wrote with j prime, and that's why I have this double summation, and I have j prime and j.
Is exponential the reverse this h?
Oh yes, I think this is, now this is correct, right? Yeah. Let me see. Yes, my notes are like prime first. Yeah, good job. Like now here you need to like, okay, this looks complicated, but it is actually not. You can like say, okay, let me fix one of them. Like for example, let me fix j prime at equal to 0, right? And write this sum. So for example, j prime is equal to 0. I'm only taking this one. And since j prime is 0, it is like this. Something like that. And when I look at this for any, like because j sum is also sum over all sides, right? All other j primes are just going to be exactly this, right? If you do it for j prime is equal to 0, the first one also is going to like, right? You are summing over all sides. Then what you can do is like you can multiply. There's like 1 over n here, this one, and there are like n different choices of j prime. So you can just write it like here. And this n is going to cancel this n, so we are going to have this form.
Plus.
Yes, I think this is plus. Yeah, this one, right? Yeah. And this one, Gerwin and Young call them like some eta of q. We are going to come to this in a little bit. We are going to like approximate these functions. So you can see like this is not normalized, right? It's a good. That's why it's a good idea to always check if things are normalized in your calculations. And another calculation is, are they orthonormal psi q prime? And this one I want to do it in like a different way. I don't want to do this summation. So what I want to do is I want to start with this psi of q, and I want to act on this with translation operator. I know what translation operator does to this object. It's going to just give e to the I qa, and I want to take it bra with a different prime, and this is going to be e to the I qa psi q prime psi q. But I can do this thing in a different way. Like I can take this thing, reverse it, right? Psi q. When you reverse, like say A, B, C, right? If you take the Hermitian conjugate, it's like C dagger, B dagger, A dagger. I'm just using this. Here, B is T, C is this cat, A is bra, and if I reverse it, cat becomes bra, bra becomes cat. So this is TA dagger, and this is psi q prime. But since I reversed this entire thing, I want to take the complex conjugate. Then this, the first line and second line are going to be exactly the same. And this thing now I can operate here. It is going to be e to the I q prime a, but I take the complex, there's like a dagger minus, there's also complex conjugate, so it's going to be plus, right? No sign. And what remains is like psi q prime. If you take the complex conjugate, this is psi q prime psi q. But we said this 1 and 2 are equal. If they are equal, I can form this e to the I qa minus e to the I q prime a times psi q prime psi q is 0. Now, if q and q prime are not equal to each other, right? If they are distinct, and we are taking q and q prime to be in the first Boolean zone in this calculation, this part is non-zero. For then this entire equation is 0. For this to happen, this has to be 0. Okay. Then even though they are not normalized, they are orthogonal. That's why we write it this form. Psi q prime psi q is delta q prime q, but if they are equal, it's going to give this eta function. Okay, this is step number 1. Now I want to calculate the expectation value of Hamiltonian. Find psi q h psi q, and for that I want to write h, which is equal to p squared over 2m plus sum over all. Let me use L notation here. L some local atomic, if you want, R minus RL, right? Something like that. But I want to act this function on a given site. I want to find H times J. And to do that, I want to take the terms that depends on site J. This is going to be P squared over 2M plus V of R minus Rj plus delta V of J. And this delta V of J is like everything that remains here, right? I just took out the site J components. Then this is going to be this thing acting on J plus delta V J acting on J. But these are like atomic orbitals, and we know like this is the atomic potential. We know the action of this, right? It is some epsilon 0 times J plus delta V of J times J. If I know what H does to J, I know what H does to psi of Q, then H times psi of Q. Also going to have this first piece, epsilon 0 times psi of Q plus 1 over root n. I'm just writing psi of Q now. This is J e to the I Q Rj delta V of J times J. Good. Now I can take bra with entire thing from the left hand side, and psi q h psi q is, this one is just a constant, and these are normalized, so it's going to be not normalized, epsilon 0 eta of q. So I take the first one. Plus, there are like 1 over square root of n coming from here. There, another one will come from here. This is going to 1 over n. So this is j prime j e to the minus I q I j prime minus rj times j prime delta v of j j. Mm-hmm. Mm-hmm.
First of all, J is orbitals of different atoms.
Yes, yes.
Okay. And H is for just one, or just an electron, isn't it?
So H is, so of course in real atom this is not the case, but we approximated it like, give me the atomic orbital, which is like, for example, for hydrogen it's going to be 1 over r, and I translated it as many times as I need for the lattice, and that's my model Hamiltonian.
And V is like a little perturbation.
The V is like this V is like, if you want 1 over r potential, like this 1 over r, and for a given site J, I like, if you want, the form is something like this. You give me this potential like a valve, and this is this site J. Full V is like this, right? You translate it as many times as you need. So this is the full V, and delta V is just, I erase this one from here. So this is not acting on the site that I'm interested in. So that's why I wrote it separately. So, and Gervin and Young calls this lambda of Q, and we are going to approximate this lambda of Q in a little bit. Then our epsilon of Q is equal to epsilon 0 eta of Q plus lambda of Q, and divide entire thing by eta of Q. And I, of course, we can write it like this. So this is epsilon 0 plus lambda of Q divided by eta of Q. Good. Now here's the point we approximate. So we need to approximate this object to be able to determine this sum. And of course, the reason we do this is we don't want to calculate macroscopic quantities like with like real potential. We want to get a model that reliably describes the solid. And for this, I'm going to define this to be delta E if J prime is equal to J. And I'm going to call this minus Y minus, because from the double val we know this tunneling has to be negative, and if J prime and J are nearest neighbors. Typically people can also put like T prime if J prime and J are next nearest neighbors, and you can take as many neighbors as you want, but generally we will not even take that. We are going to say 0 otherwise. But in some problems you can take longer and longer hopping. And if you do that, this object one, okay, let me not write this entire thing, let me copy here. So this object is going to be, first, this J prime is equal to J. This is epsilon 0. There is no exponential. There are n terms with J prime is equal to J. So then this is going to be delta epsilon plus this, if you want, minus T times, right? So this one is outside, and J prime and J are like, the way to write this is like some del vector e to the minus I q dot del. And here this delta is nearest neighbor vectors. Good. And calculation is done. A little bit redefinition to agree with Gerwin and Young. For eta of q, we can also do this approximation with like nearest neighbor tunneling. But this is because it's in the denominator, the tunneling will be a higher order effect. So the eta of q will be approximately 1. Right? There's like, if you want dot 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 terms that may depend on tunneling, but for small tunneling, we don't need that either. Then epsilon of q is going to be equal to some constant, let me call it a, we don't care, minus some other constant, let me collect everything here, is going to be like phi of q.
Can you explain the justification for eta of q being approximately 1?
I think, let me start from here, yes. So this is the eta of q, right? Let me just take this here. So let me erase that. So exactly like, okay, here we are saying that J prime and J are like, at some point we have to approximate that. That's the approximation we did. And now I look at this. Here's like some Gaussian at, if you want, Rj is equal to 0. And I look at another atomic orbital at J's side, right? So this is also Rj. And typically their overlap is very tiny, right? Because they are like located at different sites. Then I can say that if, okay, I can say that this is 1 if J is equal to 0. And some very small number, I think Gerwin and Young use zeta if J is equal to, for example, 1, nearest neighbor. You can put eta prime if J is equal to 2, but typically we just ignore this, right? This is like 1, right? This is 1. If this is 1, the entire thing is 1 plus some small number. And the reason we like didn't even consider this is like this is in the denominator. Something small in the denominator will come with like higher power if you do this Taylor expansion. So at the end, let me just write result, and this is, you don't need to remember all of these calculations. This is the part you need to remember. At the end, you have something like this, right? E of Q, some constant, we are going to drop this, right? Overall constants, we don't care about it, right? We can put the zero of energy wherever we want, right? Potential is not observable. We can shift it up and down any way we want. So this is going to be dropped. Minus, if you want some 2t, this is the nearest neighbor hopping, and it's going to be sum over all nearest neighbor vectors, e to the minus I q dot delta. Okay, I apologize, this took a little longer, but let me give very quick 2 examples and then I'll finish it here. So, example. So in 1D, of course, if you have to leave, you can leave, I don't mind, but I'll give you 2 examples here. In 1D, suppose I have this, and I have only 2 nearest neighbor hoppings, right? I think this is maybe something like, let me write it like t, and I'm going to fix it. So I can hop it like this, and I can hop it like that, and this delta e to the minus I q delta is going to be, my delta is a times x if you want, and it's going to be I q a plus e to the minus I q a, and this is 2 cosine qa, right? That's why now I know the potential, I can write the dispersion, and I'll write it like this, cosine qa. So I can do it in 2D. So here is the square lattice. Now I have like a times x. This is a times y hat. And this object, let's write this sum over all delta e to the minus I q dot delta is going to be, I can do this cosine in x direction, right? This is minus 2t cosine qxa, or I can do it in the y direction, minus 2t cosine qya. And that's why we had this earlier. I was saying that I can write the spectrum like this. This is where it comes from. So as an exercise, actually let me do the confusing one and give you the trivial one as an exercise. Suppose I want to put the next nearest neighbor hopping. So this is what people generally get wrong. So here's hopping like this, and hopping like that, and hopping like that, and hopping like that. Let's put t prime to parameterize this hopping. And the spectrum is going to be E of Q, exactly this same thing, minus 2t cosine. Let's take, let me write it, cosine QA plus cosine QYA. So this is the next nearest, this is the nearest neighbor hopping, plus 2t prime. What do you think? So here's the vector, you need the sum. What should the argument of first cosine be? Huh? A times square root. And what about the momentum?
Sum of them.
Exactly, yeah. This is the, yeah. Maybe let me give you the answer, you can write it yourself. This is going to be qx plus qy times a plus cosine qx minus qy times a. And this is many parentheses, but sorry about that. If you want, you can take longer and longer neighbors. We are not going to do that. Another exercise. Do it in 3D, right? There will be qx, qy, qz, and also like find epsilon of qx, qy, and qz. And it's also a good idea to draw in Mathematica. Draw in Mathematica, and you are going to see like these bands people show in the textbooks that looks kind of weird. But as you like, what you need to do is like you need to choose equal energy surfaces. if the equal energy surface, the energy you choose is very tiny, it's going to be like a ball. At some point, it's going to change from like a symmetrical ball to like something like a cube, and that cube will deform. And then if you see that, I think you are going to understand why people have certain like three-dimensional pictures in, for example, Ashkov-Mermin's cover is the result of this picture. Okay.